Hello everyone. Welcome to today's webinar. I'm Faye. I'm going to deliver the webinar talking about the deep learning on Sharcnet best practices. Okay, so during this webinar, there are three topics I want to discuss with every of you. So the first one is what does Sharcnet have, and I'm going to introduce our hardware and the software resource now and in the future. So second, I'll give you a very simple example to show you how to run a deep learning job on Sharcnet cluster. I will use the Torch 7 as the tool to demonstrate the example. And the next one is I want to show you how to do the deep learning training the neural network in parallel. I will show you a Theano-based MPI framework developed by the student, and I help the student to develop this framework. I'm going to show you how to run it in a multi-GPU cluster, so you get a performance improvement when you add more GPUs to solve your deep learning problem. At the end, I will just discuss some other considerations like I/O considerations or any other considerations you want to talk in the last part. And I will show you I/O example showing you why a lot of people find the cafe is running very slow on Sharcnet environment. Okay, so let's move to the first topic. So the hardware resource. Well, main GPU systems are listed here. So our very old GPU system Monk, which has old GPU type and the 100 GPU number. I wouldn't recommend you to still using this old GPU because it's very slow and it doesn't support the newer libraries like cuDNN and something like that, but it's still usable for lightweight Theano job. And I'm afraid that Theano is the only framework that support the old GPU nowadays. And other frameworks like TensorFlow or something that it requires cuDNN to accelerate the convolution neural network on GPU, so that requires newer GPU architecture. So, and next to cluster are all contributor clusters. So we got a Copper for multi-GPU jobs that contains 4 Tesla K80 cards. That is 8 GPU chip or device per node, though in total 64 GPU devices, and is suitable for single GPU, multi-GPU, and a distributed network, distributed work. And Mosaic is another contributed cluster that equipped it with K20 GPUs, and we got 20 nodes, and each node has 1 K20, and that will be suitable for single GPU and distributed multi-GPU job. So next we're going to have our big cluster GP3, and it will be available around April this year. That will equip the newest Tesla P100 GPU, and we will have more than 300 GPUs available for everybody to use. So this is suitable for the single GPU and distributed GPU jobs. So we also have some experimental system, and we have the IBM Minsky box, and it will be available coming online very soon. And that equipped the NVLink version of Pascal P100 card, and there are 4 P100 each box connected with NVLink, and it's for testing purpose. It will be online very soon, and we will have the system page available, so you can take a look at the system and find a way to access it. Okay, so the non-contributors if you are non-contributor and you want to run it on a contributor cluster, that you have a 4-hour limitation. But I don't really think it's a problem for deep learning research, because most of deep learning research, when you train a neural network, and you can always do the checkpointing. So you do a checkpointing and then make it run 4 hours, and then you resume the training and run another 4 hours. So you keep running longer time on this contributor cluster, even you are not a contributor. Okay, so in our cluster, all our cluster are using a high-speed interconnection InfiniBand. So it will be good for if you want to train your neural network in a distributed ways. So you will find more information about the softwares on. We got a special page called Machine Learning and Data Mining, and I will show you later how to find the page on our help wiki. In that page, I have the software available. All the software are available listed. So you will see Cafe, Torch, and Theano, TensorFlow, and NVIDIA Digits, something related to deep learning. And I'm going to continue adding more software, the popular software, into that page. Okay, so besides the GPUs, there is another thing that is very important to deep learning, that is the I/O, is a file system. So as you may all know that we have homework in Scratch, so you learn that from the user training seminar. So, and here I want to mention another place to hold the data. It is called a temp. So temp is the local disk on each node, so it's only accessible to within a node. And why do I mention temp here is that in the future, in our big cluster, we will equip SSD each node. So it will give you the best performance if you have all your training data on the local temp that is on SSD. So I will talk about the I/O later. So data transfer node is somewhere you can transfer your data to Sharcnet system, and it's the internet, and there is no CPU time limitation. Because you can also use the logging node to transfer the data, but deep learning data, if you want to transfer the whole ImageNet data set, that is more than 200 gigabytes, you may reach the CPU time limitation on a logging node. So you don't want to see the system cut you off. So you go to the DTN node, and there is no CPU limitation. You can upload your data in the days. So, and there are some storage limitation and enforcement, and I believe that you all know that. Okay, so managing job with SQ is the same thing. I copied these slides from user training seminar just in case some of you haven't taken the user training seminar. So that is, I want to make it short. I just want to mention that the SQ, all jobs should use SQ sub to submit to a cluster. So it's not something like you running on your own desktop. In this SQ sub, there are some flags that you want to put after the SQ sub command, and -r means runtime, so you can specify how long you want to run your job. And if you are not a contributor and you want to run a job on the contributor cluster, so you have to set the -r within 4 hours. And GPU jobs has to specify the Q GPU, and if it support MPI, and we're gonna show you later that you can combine MPI threaded CPU with the GPU jobs using the -f. And you should also specify how many CPUs you wanna use. and you also have to specify the number of GPUs and the memory size you want to use. And here I want to talk a little bit more about how many CPUs you want to choose, because different cluster has different architecture and has different topologies with the CPU and GPUs. So some cluster you may find that within a node there are 8 GPU devices but only 16 CPU cores. That is, you only have 2 cores per GPU. So for each of your GPU job, you'd better not to ask more than 2 CPU cores per GPU. Otherwise, you will waste the GPU resource if you ask the whole node of CPU but only using 1 GPU. That you waste 7 GPU in the node. So you just keep this in mind and choose the proper CPU number of CPU with your job. Okay, so you got a SQ job for checking the job status and SQQ to stop or queue the running or queued job. Okay, so let's move to some example. So the first one I want to show you is the Torch 7 example. So a lot of you may know that this neural algorithm artistic style that is very popular last year. You got some iOS apps that support you upload your image and they just combine the style and generate a new artistic styled image. So next I'm gonna show you how to get this work done using Sharcnet resource. Okay, so well, if you got a job to run, so what's the steps you are going to follow? So the first one is you have to get the code ready. So you can get the code on GitHub, some other's code, just download some other's code, or you can write your own code. And the next thing is to prepare the data. So only the login node have access to the internet. If you need to download some example image or some pre-trained network parameters file, and you can only use the login node or the DTN nodes to get the data ready. If the data is large, just use the DTN node to get that data. And software environment is very important when you use the software packaging on Sharcnet, because we installed the software package for user, but we're not installing it into the system default path. So if you are in the Linux environment, if you want to find some file, you have to tell the system where to find that file. So if you we install the software, we put it somewhere else special. It's not the system default. So the system don't know that you got a Torch software installed in somewhere. So you have to set up all the environment. Well, the environment variables includes the path that is telling the system where the file is, and it also tells the system where the libraries are. So, well, to make it easier for the user to use it, I prepared all this script in a script format for all the deep learning tools. So that means you only run one script. In this script, it will set up all the software environment and all the path to libraries and the files. So I will show you later that it is very easy to do. So once you set up all the software environment, once you get your code and the data ready, then you just submit a job. So submitting the job, you have to choose the number of CPU and the GPUs, memory size and runtime. So please don't ask more than you needed. As I explained before, if in a node with 8 GPUs, that you're asking for all the CPU resource, but using only 1 GPU, that means others' job cannot be assigned to that node only because all the CPU resources have been assigned to you. So you're wasting 7 GPUs. So you just use the appropriate CPU number of CPU per your GPU job. And you can find more information with this link, and I will give you a demo now to show you how to find all this information on Sharcnet website and how to interact with the Linux command to get the job done. Okay, so this is our help wiki. So once you go to this help wiki, and you will find new to Sharcnet card here. So there was a link called domain portals. So you go to this domain portals, you will see different domains. So just follow the link, machine learning and data mining. Then you go to the page contains the software packages information. So you will see Cafe, Theano, digits here. So we want to use Torch. So you go to the Torch link here. It's got a user guide, so Torch wiki. Then you go to the Torch wiki. You can see I got some topics here. So running Torch 7. And I also got an installation guide if you want a different version of Torch, or if you are developing Torch, you modify Torch, and you want to get things installed. So you follow the instruction of how to build Torch by yourself. I also got some extra information about using the Lua rocks to install packages. Okay, so let's move back to the running Torch on Mosaic and Copper. So that's very easy. I got everything ready set here in the script called Torch Activate. So Torch Activate contains all the script or all the command that's needed to set up the environment. And I also got a summation command example here. So that is submitting the serial CPU job. Okay, so let's switch to the terminal and get you the example running. Alright, so I've already downloaded the NeuroStyle from the GitHub. So you can see there is a .git. So I just clone the repository to my own folder, and you can see here I'm on Copper login nodes. Okay, so the first thing I want to show you is once you get this Git repository, and well, it depends on the different model you are running. This model used the pre-trained neural network parameters. It actually is using the VGG, a pre-trained VGG9 Cafe model. So you go to the models, and then you will see, and I got the VGG 19 model downloaded. So I downloaded just in the login node using the script. So this repository gives you the scripts to download all this model. So you get all this model ready, and you can have your own files, input files, and the input images and the style images. So, and let me show you what this input and the style images are. So this is the input image, and this is the output. This is a style image. So we want to combine these two images together. And I've already uploaded this onto Sharcnet, so I should be able to just run the command. Okay. Alright, so let me show you what the command looks like. Alright, so as I mentioned before, if you are in a Sharcnet environment, for example, I just want to log in. just want to log in. Once you log into the Sharcnet, you got everything loaded by default. So if you check the modular list, they use the old Intel compiler and old libraries. So how can you, well, if you want to run torch, the system cannot find where the torch is. So you can say, okay, I want to check where torch is. So the system will show you, all right, there is no torch. But after you run the command, source the command I mentioned before, and the system should be able to find where torch is. So you will see, okay, torch is under the option opt/sharcnet/testing torch. So then you should be able to, now you should be able to just run torch directly. So if you want to train this neural network, you gotta, well, you have to set the command you're using, you want to use, and you can go to the website to see how other people run this command. I will just show you this easy command. So in this command, you will see we got a th, that means torch. Neural style is the code. Actually, the code is running with torch, and you got some parameters like input style image. You got an input image, and you specify output image, and also some other flags like a number of iteration or something relatively initial image. All right, so well, if it's on your own desktop or your own computer, so you just basically run this command directly and you get your things done. But on Sharcnet, you have to submit this command as a job to the scheduler. So let me show you how to schedule this. Well, once you set up all the environment on Sharcnet, it will be automatically passed to the job. So all the jobs you submit are using the same environment settings as you set before you submit this job. So you just submit this command. That is fine. You don't have to run the environment settings or setting all the path again, because all this path will be passed to the job. So we're using the SQ subcommand to submit to a GPU queue. So because this job doesn't require multi-CPU support, so I'll just submit it into the serial queue using only one CPU with this job. And well, I have to pick up how many GPUs to use. So for this job, it's only one GPU. So I got a GPP equals 1. And I set up a memory. So how to choose the proper memory? Well, it depends on how much memory each node, right? So you want to, for example, this node has 96 gig memory, so that is 12 gig memory each GPU. So that is equal to the GPU graphic memory size. So, but for this job, probably 4 gig or 8 gig memory, that is enough. But just in case it used a larger memory, so we set the memory to be the same amount of GPU graphic memory. So for this K80 cards, and for each K80 GPU device, there is 12 gig memory, and you can set up 11.5 because it's ECC, so you got a half gig less. And I also specified where the output file should go. So then I'll just submit this script run.sh, which contains all the command above, th, neural style, something. Okay, I forgot runtime limitation. So this is a very short job. I'll just say, okay, I want to run 1 hour. Okay, so once the job has been submitted, you can use the SQ jobs to check the status. So you can, once you get the job running, and you can log into the node to see how it's running. So for example, if we say NVIDIA SMI to check the GPU status. So you guys say, I got one job. This is the last one on GPU 3 is my job using the torch. So it's running now, but you cannot see the whole thing, right? You see all this. So you got one job running on GPU 3 using like 3 gig graphic memory. So it's not using all of them. Okay, so let's get outside and take a look at the output file. Alright, so the neural network is running. So you see all the output from the job. Okay, let's just leave it there for a couple of minutes until. Okay, so moving on to next topic is multi-GPU training. Well, sometimes you may find deep learning model is getting bigger and bigger, deeper. The neural network is getting deeper and deeper, and it takes months, or even some model even takes a year if you're running training it on your single GPU. So that's the people are thinking of using multiple GPU to train a neural network at the same time to accelerate the training process. And I believe a lot of deep learning architecture or deep learning tools or frameworks now support the multi-GPU training. For example, NVIDIA has multi-GPU cafe support, and Google TensorFlow natively support multi-GPU. And Torch and other Theano, they all get a multi-GPU support somehow. So, well, if you want to training a multi-GPU job, so there are something you have to think about. So there are 2 different kind of parallelism you can do. So the first one is the intra-node parallelism for the node with multiple GPU, like Copper. So we got 8 GPU devices in Copper, so you can do intra-node communication with all these GPUs. And also you can do inter-node parallelism for the GPU nodes with high-speed network, like InfiniBand network. And for all the GPU clusters that are equipped with the InfiniBand network, then you can do inter-node parallelism. And also you can combine these 2 methods to make it not only use all the GPUs within a node, but also use the GPUs on other nodes. So I'll give you an example of the hardware layout of Copper GPU. So you will see in a Copper GPU node, and we got a 4 K80 card, that is 8 K80 devices, and it also equipped with the InfiniBand, so you can have multiple Copper GPU node working together. So next I'm gonna introduce Theano-based distributed training framework that is developed here in University of Guelph, and I helped the students and researchers to develop this node using MPI. So you will see our results is if you want to train a GoogleNet and by using multiple GPUs, by using 8 GPUs, it gives you more than 7 times speed up. So it greatly reduced the training time. So next I'm going to show you how to submit a multi-GPU job on Copper cluster. Alright, so the same thing. If you want to run, well, if you want to run Theano, then Theano is a Python-based framework, so you have to let the system know which Python you're going to use. Well, if you do which Python, by default, it's a system default one that is very old that doesn't support Theano. So if you go to the Theano website, our document about Theano is not Theano official website, and you will find the way to run Theano. Just very easy, just using one command is source. We got an opt Sharcnet testing set for Theano new. So set for Theano new is using the Theano new backend. Well, if you are familiar with Theano, you know that they moved the old backend to a new backend, the PyGPU backend, and they get a better performance and make things easier. So here I'm using the Theano new backend. So let's take a look at what's inside this script. Then you will see all what I do for setting the environment. Okay, so here you will see we got a couple of commands to run. So the first part of this is to change or switch the modular, because we're using the newer Python, so we have to get all the dependencies ready for Python. And we also have some MKL related citing. This path citing will help the system to find where the executable file is, and the LD library path will help the system to find where is the Theano new backend libGPU array library is. And also we're using the NCCL library to do the multi-GPU communication within a node. And you also find where the cuDNN is. So that's everything about the environment path citing. So after you got all this running, and you should be able to find the Theano package and all the dependencies you need in our Sharcnet testing folder. Okay, so just do the same thing, and you just download someone's code here, and you just follow the instruction. Follow their instruction how to use this code. And you got some command, for example, here, and well, follow the instruction. You just run a BSP worker sh, and you specify a number of GPUs. That is how you run it on in your own computer. But for Sharcnet, we have to use the SQSub. So SQSub, we're going to put it into a GPU queue. Well, because it's an MPI-based framework, so you have to run it into the MPI queue. And you specify, okay, I want how many CPU cores I want. For this framework, it will use all the CPU resource within the node. So I'm only give you an example for asking for one node with 16 CPU cores, and you ask for 8 GPU. So the number of the memory you want to use. Well, here's the tricky part. In Copper and Mosaic using a Slurm, so there is some different when you're asking for a memory. So we have something different in SQSub. So in Copper, in the --mpp will translate it to how much memory you want to use in a node, not each MPI process. So you have to ask the whole memory, I mean in total size. So this node has 96 gig, so 94 gig memory available, so I'm asking all of them because I'm taking over all this node. In the run BSP script, there is a built-in MPI run command. So I don't want a system or SQSub to launch MPI for me. So I'm using --no MPI run because I'm launching MPI by myself in the script. So I tell the SQSub command not to put the MPI run in front of my script. Okay, so I also have to specify how much time I want to use in the output file. Okay, alright, so I missed one space here. Okay, so I gotta drop submit. So it's running on COP2, so we can just log into COP2 and take a look at the job. Okay, so if you do a top, you will see we got multiple Python processes running, and each Python process is controlling one GPU. So if you do a VDSMI, so you will see we got 8 Python instance for 8 GPU. Okay, so different multi-GPU framework uses different way of communication, and this example uses the MPI, so you have to put it into the MPI queue. If you're using TensorFlow, that is using threaded, but not using MPI, so you put the TensorFlow. When you submit the TensorFlow job, you just put it into a threaded queue. You just use -q GPU -f threaded, and you're asking for the number of CPU you want to use. Just the same thing. Just go to our help wiki, and you will find all the related deep learning tools and how to use them, instruction of how to use them. Okay, so the last topic I want to discuss here is the I/O consideration. So I got some people sending an email to me asking why in cafe you see the waiting for data, and sometimes you see a lot of waiting for data between each iteration. So that is a wasting time that people measure that the waiting time is 80% of total training time. So that means you are limited by the speed of waiting the data from the file system to the compute node. So we all know that the faster training needs faster I/O. So for example, if it takes 2 seconds to load the data into the compute node, and it takes 5 seconds to compute this data, so you will not have a problem if you can overlap the loading and the computing. But if once we get a newer GPU that is 5 times faster than this K80 cars, and you got a less than 1 second training time, but it takes you 2 seconds to load the data, you cannot overlap this. You are still wasting time loading the data. So that in that situation, you have to choose a faster way to get the data from the file system to the compute node. And which is faster, work or temp? Well, in our user seminar, we suggest you to copy your big data or data that is big to work, because we give everyone one terabyte data quota on work. So a lot of people just store their data set in Word, but people have no idea which one is faster, work or temp. So let me tell you, the work is fast, and because the work server is a parallelized file server, and is equipped with 10 gig work. So you will probably can reach 1 gigabytes per second. That is very fast file system. But why Cafe is still waiting for data? And what happens if data are not temp? So temp is, well, on copper, take copper as example. The temp disk on copper is just a spinning disk, and it's only around 100 megabytes per second. I believe it's slower than some of your laptop or desktop which equipped it with SSD. And why running it on the spinning disk shows no problem, just like the picture above. you don't see any waiting data output there. So why and temp is which only have 100 megabytes per second speed works very well for cafe, but work which can achieve 1 gigabytes per second cannot satisfy the cafe's I/O requirement. Well, the reason is that when you train your neural network, you may know that you got a mini batches training one by one. So how can you pick up the mini batch? You do you randomly pick up the mini batches and put it into your model to train your model. So the random access speed is very important for a framework like Cafes using one LMDB dataset, and because you want a random access within one file that is very slow on a remote file system like Work and Scratch. Even it can achieve 1 gigabytes per second, but this is for continuous access. It's not for random access. Random access performs better than in a spinning disk. So the best way to solve this problem is we move the data set from the work to the temp. So then there is a question of what is the best way? How can we move the data from work to temp efficiently? So before I answer these questions, I want to just talk a little bit more about the parallel file system, which is our work. So our work server or Scratch server is using Lustre file system. So Lustre file system is look like this. So you get a multiple. Well, let's just ignore the MDS. We get a multiple OSS, and each OSS has an OST. So OST contains a lot of disks. So once you want to read the data, then you pick up the data from the OST. OST is the somewhere that stores the actual files. So by default, a single file is stored in a single OST. But you can also stripe the files across OST. That means you can have one file, but it's being stored in different OST. And once you access that file, it will give you the file in parallel from different OSS and from different OST. So to set this, the command is very easy. You got to use the LFS Lustre file system set strap, and -s means strap size, and -c means how many OST you want to use for one file. And then you use the copy command to copy your real data into the file you created, well, the empty file you created. And you can use the LFS get strip to check. Okay, so you can find all this information on Sharcnet help wiki. So you can just, I will show you that later. It's very easy to find all this related information at our help wiki. So let me just give you the result. So the performance with the strap and the size and the count. So for this test, I'm copying 9.4 gigabytes from work to temp. Actually, it's an ImageNet validation dataset. By default, I reach only 70 megabytes per second. So this three numbers is that I did this test 3 times. So it shows different speed because of the different network conditions. So this is 3 different tests. And if I put one file, well, 1M means 1 megabyte strap size. 2C means I got a 2 OST for one file. So if I put one file onto 2 different OST, I can get 136 megabytes per second. It's nearly double the performance. If I put it into 4, and it give me even better performance. If I put it into 8, it give me the best performance. If I increase the stripe size, it will slow down. So you just Then I give you some tips for this. So you keep the strap size to be 1 megabytes. That is the default one. And the strap count can be between 4 to 8. Well, it depends on how big your file is. If you only get a 1 or 2 gigabytes each file, you probably should use only one OST. So set the count to be 1. If you get like a 10 gigabytes, you can set it to 2, 4, or 8. So you can do a test with a very large data set, like if you copy the whole ImageNet training data set, which is 200 gigabytes, then you probably should want to use 8 strap count to put this file onto 8 different OST. So work file system is really for large files, sequential read and write. So temp is for small files and a random access to a large file. And if you want to, because the work is for sequential read, so if you want to copy like images, for example, you want to have the whole ImageNet image, 1 million image copy from work to temp, and you'd better just to tar them in a single format and copy them once instead of copying each image. That would be very slow. It takes days to finish this copy. If you copy only one single file, one single tar file contains all the 1 million image, it will take only hours to finish. Okay, so multiple copies of common data set on every node without expiry. Well, this is because Copper cluster is basically for deep learning research, and the contributor research group, they require us to access ImageNet dataset every node. So I got a copy of ImageNet on each Copper's temp node without expiry, so it's not created by you. If you created file in the temp, and you will have 7 days or 2 days expiry. It depends on different cluster, but we can put the copies of a common data set, image set on each node. So I want to talk a little bit more about this temp, because in the future, once we get the GP3 system, our big system, and each GP3 node will be equipped with the SSD, and that is more than 1 terabytes storage size. So we will have the common data set ImageNet on directly on that SSD. So if you want to use this ImageNet or you want to use the other bigger data set, you can just ask us to keep a copy on each node. Then you should be able to access this data set locally, not using the remote file system. Okay, so that's basically everything I want to talk today.